Welcome. This video is for students going into Algebra 2, and it is meant to be a review during the summer so that you can keep up with your math skills or maybe get back some of your math skills so that when you start your Algebra 2 class, you're ready to build on this foundation that you should have started in Algebra 1. So what is more iconic from Algebra 1 than solving equations? Nothing. Nothing is more iconic. So this first section has us solving equations, and these do not all look the same. They do start off very easy and get progressively more difficult, or there's just more steps, I would say, is the real difference between these problems. So number one, you might be able to do this in your head by saying, well, what plus 6 equals 7? That's a really easy question to answer if you think about it. The way we do it algebraically and show our work and why our answer is the way it is we say that plus 6, we're going to subtract it from both sides to move it over. And so that confirms for us algebraically what we might have already known in our head, which is that n equals 1. You can leave it like this with the 1 on the left side, or if you wanted to rewrite it so that it says n on the left, either of those is fine, whichever you'd like to do. So we have this idea of doing the opposite to move things over to the other side of an equation. Perhaps, again, you can think negative 11 plus n equals negative 10. What does that mean n has to equal? What would I fill that blank in with? Or if you want to use algebra to do this, you'd say that negative 11 needs to get added to both sides. That negative 11 plus 11 is 0, but I can't just do it on one side. I have to do it to both. So that means that n equals negative 10 plus 11, which is 1, positive 1, because the 11 is the bigger number. Weird that those are both 1s. Coincidence? I think so. All right, number 3. I believe this is a negative 4 on top, although it looks a little smudgy on my screen. Hopefully not on yours, but probably on yours. Negative 4 plus r divided by 14 equals negative 1. Now, a lot of people get freaked out about fractions, but fractions are just a fancy way of saying division, or even actually kind of a nice way of saying division. If we are doing negative 4 plus r divided by 14, we can get rid of that divided by 14 simply by multiplying by 14 over 1. That would cancel this and this. But since it's an equation, if we do it on one side, we need to do it on the other. On the other side, where we're doing negative 1 times 14, we don't really need the over 1 anymore. We just need to think, what is negative 1 times 14? So we have negative 4 plus r equals a negative times a positive is a negative, so that'd be negative 14. And now this negative 4 we're going to add over to the other side. So plus 4 and plus 4. You definitely, at the point of being in Algebra 2, want to be able to add and subtract numbers. So negative 14 plus 4, you subtract those and get 10, but it's a negative 10 because the 14 was the bigger number. Number 4, now this is kind of what I think of as an iconic sort of Algebra 1 equation because there are 2 steps to it. One is moving the 6, one is moving the negative 3. The order of operations for solving equations does go backwards from normal order of operations in that we want to actually add the 3 first because it is, I would say, I like to call it like farther away from x. The 6 is right next to x. They're like multiplied together. They're so close to each other. So we actually want to start with the things farthest from x first and then move closer to x as we solve. So we add the 3 over. Negative 90 plus 3, we subtract and keep the negative. So that's negative 90. When I divide both sides by 6, this is kind of a big number, but it actually does work nicely. Make sure you don't forget that since it's a negative divided by a positive, we get a negative answer. 6 goes into 9 once with 3 left over, so 6 goes into 35 times. So x equals negative 15. On all of these that we've done so far, you could check your answer by plugging back in. So I could come back up here and do 6 times negative 15 minus 3 equals negative 93, and that would tell me that this is negative 90 minus 3, which equals negative 93. For my answer. So I've confirmed that that is the correct answer. Number 5 and 6 have parentheses, so they're, and 7 and 8, And so as we're looking at these, there are a couple different ways we can go about this. So I can distribute the 5 to both things in the parentheses here, or if I want to, I could divide both sides by the 5 that's in front. When we are dividing, and there are two things on top like this being multiplied together, we actually get to pick which of these two things gets divided so that that cancels. Whereas if there's only addition on top, like if our problem was like this, no, we're not allowed to cancel those 6's out. We'd have to cancel from everything. But if we instead have this situation, yes, I can cancel those 6's out. So you got to be careful when you're trying to do that and know when you're allowed to cancel and when you're not. Here we're allowed to say, well, everything's being multiplied by 5. Let's just divide the 5 over. That leaves us with 6 plus 4a equals 110 divided by 5 is 22. And then we would continue solving by subtracting and dividing. You can totally use a distributive property on this. And in fact, on the next one, I'll use the distributive property, even though we can also just divide on the next one as well. The times where dividing is not helpful, and I would suggest you not doing it, is if you have more things. Like for instance, on number 7, dividing by this -1, right off the bat here, you might forget to divide everything. So I'd say if there's something else next to the parentheses, maybe distributive property is the better way to go. Or if you're trying to divide and it gives you fractions, then I would say distributing might make it easier. That doesn't happen on either of these, but let's say that this was a 7 instead of an 8. Well, I would say distribute. You're going to end up with a fraction as an answer because of trying to divide things by 7, but at least the fraction you end up with happens later. So when you see parentheses, there are technically two options. Yes, you can use the distributive property, but if it's just the number in the parentheses on the side by themselves, you can divide by the number in front. And I would say that that's slightly faster if you realize that that's something you can do. So on 6, I'll go ahead and distribute in case that's your preferred method and you want to remember how to do it. We would do 8 times -6m, which is -48m, and then we do 8 times 6, which is +48, and so that's equal to -96. Then we would subtract 48 over and get a negative number. 6 and 8 together makes 14, so that's 144, and it's negative. Make sure you keep track of that negative. Now here's why the distributive property is the slightly more difficult way of doing this than just dividing the 8 over, is now we have larger numbers to work with, whereas if we just divided everything by 8, we have smaller numbers. I would take a wild guess that this is 3, and then probably come over here to the side and multiply out to make sure. Yes, 48 goes into 144 3 times, and a negative divided by a negative is a positive, so m equals +3. So here on 7, yes, you can divide by that negative, but I would suggest at the very least that you subtract 8 over before you do that. But if you're going to distribute, then that's actually not the best first step. If you're going to distribute, then you might as well distribute. When you're distributing a negative, it is like distributing a -1. So -1 times r is -1r, or just -r. -1 times 3 is -3. So it would turn into this, and then we could say -3 plus 8 is 5. And then we could do, it doesn't matter which direction you go. I like to make things as positive as possible in math and in life. And so I would therefore add the r over. Oh, I guess no matter what, you end up with a negative here. Subtract the 37, so you get -32 equals 4r. So then divide both sides by 4 and get a -8 as our answer. On this next one, I guess I can do another one where we divide here, because if you look at this and say, should I divide by -5? The way I would say to decide is do both of these divide by -5, because whenever it's subtraction or addition, like how this is, both things have to divide. If we're going to choose to do that step, we need to do 5 divided by 5 is -1m. -20 divided by -5 is +4. And that cancels, and we have -6m minus 1. So that is an option. You can do it that way. And so just in general here, once we started at number 5 and looking at 5, 6, and 7, there is definitely more than one way to go about this. All of it uses the same sort of rules of how to do it, but maybe there are different orders you can do things. And so if you got the same answer a different way, there's a really good chance that you did it right. It is hard to get the right answer with the wrong method, but there are times where you may look at the answer and say, oh, I know how we got that, and because of working backwards or whatever, have invented some math rule that got you there, which that's not good. Don't invent your own math rules. I'm going to add 1m over to the left. It does not matter which way you add or subtract the letter and which way you add or subtract the number. You just want letters on one side, numbers on the other. So this is -5m equals 5. So I would divide both sides by -5 and get m equals -1. So what I was saying earlier is if you looked at the answer key and saw that the answer to this was -1, and you're like, oh, well, that's probably because there's a -1 here. Well, that sort of logic is not really great to use. But if you did the problem and you got m equals -1, and you did similar things to what I did, but maybe not exactly, or maybe you used the distributive property, which I didn't, but you got -1, you probably did it right. And so if you're really nervous about whether or not what you did was right or not, then try to find more problems like this to practice, either with the help of the internet or a friend or sibling or parent or someone, so that you can figure out if you really have the right idea or not. Let's solve some inequalities and graph their solutions. Now, when we solve an inequality, it's very similar to how we solve an equation. The main difference is that we do have to keep track of what the inequality is, because the direction that our inequality is pointing matters to show which side is bigger and which side is smaller. And we also have to keep in mind that if we multiply or divide by a negative as we are solving, then that means that we have to flip the inequality around. And it matters that we're multiplying or dividing by a negative, not with a negative. So it actually isn't going to occur to us on either of these, but if you have something like -3x is less than or equal to 9, if you're dividing by -3, the bottom number here is a negative. That's what makes us flip the inequality around. Okay. The other thing is that we're solving, so we should end up with an inequality for our answer, but we're also supposed to graph, and so that means that we'll end up filling in on this number line either a closed circle or an open circle, and then shading to show which way our answers are. So if I have x minus 14 is greater than or equal to -30, I'm going to start by adding 14 to both sides. And that's exactly what I would do if this was equals instead. X is greater than or equal to -16. That is part of my answer. Even if I graph it correctly, if I don't have that answer, then it's not completely right. Because solving this, we want to show it both ways. So now when I go to graph it, I look at the inequality, I say it's greater than or equal to. Equal to means to put a filled in circle, and greater than means that I need to shade the numbers that are greater than -16, which are numbers like -15, -14, 0, which would be way over to the right of this number line. So I'm going to shade to the right and put an arrow to show that my solution goes on forever. There's a cool trick you can do to know which way to shade, that if the variable is on the left side of the inequality, then it's like the inequality is an arrow pointing you the direction you want to shade. So imagine that this inequality is an arrow, that arrow would point to the right, and that's the direction that we shaded. That only works if the variable is on the left side. If it's on the right side, you would need to either flip it around or just think, oh, it's backwards from the way I normally do it. On 10, we want to add 16 to both sides. So that means that n is less than negative 28 plus 16 is negative 12. That is part of my answer. And then because it's less than but not equal to, I'm going to put an open circle that's not filled in. That shows someone looking at this answer that negative 12 is not actually a possibility for my answer, but all the numbers that are less than negative 12 are, which are the numbers to the left of negative 12. In other words, this direction. So that's some inequalities for us. Now we're going to sketch the graph of some lines. So this is another very iconic Algebra 1 thing to do. And this one is in y equals mx plus b, which is also known as slope-intercept form. And in slope-intercept form, m is the slope, and we usually make it into a fraction. B is the y-intercept, and it is also what we begin graphing with. So we're going to take the negative 3. It's the y-intercept, so we're going to put a dot on the y-axis. And then our slope says 2 over 1. Slope is rise over run, which in this case is 2 over 1. So we're going to go up 2 over 1. Now, depending on who your teacher is, maybe they're happy with 2 points. Maybe they want you to draw lots of points. I personally am okay with 2 points, but I know that I draw better lines when I have more points, and the squiggliness of this line is caused by the fact that I am using a computer to do this, and that makes it harder. So pretend that this is a straight line and use a ruler if that helps you, but your teacher is going to be looking at your points, particularly the negative 3 on the y-axis and then the up 2 over 1, or up 2 over 1 is the same as going down to left 1. So you also could have used this point and this point. That's what your teacher's going to look at more so than like how perfectly straight your line is. If our equation is not in slope-intercept form, typically what we do is change it to slope-intercept form because it is actually probably one of the easiest ways to graph. So that means that we need to get the y by itself. So we'd subtract by 3x and get y equals negative 3x plus 1. So our slope is negative 3 over 1, and our y-intercept is positive 1. So here is positive 1. I'm going to go down 3 and right 1, or because this is a negative 3, it could be that I should go up 3 and left 1. Having a negative number and turning that into a fraction means there's a negative either on top or on bottom, but not both. So down 3 over 1, or up 3, 1, 2, 3 over 1. So something like this. And there is our line. That is graphing lines or linear equations, because here we are graphing linear inequalities. Now, this first one is actually really similar to what we just graphed, except that it's an inequality, and whenever it's an inequality, you do pay close attention at the beginning to whether or not it's equal to or not. Because if it's equal to, it's a normal solid line. If it's not equal to, we draw a dashed line. So as I'm graphing this, I want to start at negative 1. I want to go down 3 and right 1, up 3 and left 1. But I want to draw a line that is not completely solid, because I want someone to look at this and say, oh, the points on this line are not a part of the solution. When we're doing this, if it's solved for y, and we're graphing greater than, we would want to shade above this, because we want to graph the points that for y are greater than this line, and y is up and down. Now sometimes that can be tricky to decide which side of the line is above and which side of the line is below. I have a foolproof way to figure it out. And that foolproof way is to put your pencil on the line that you drew anywhere you want to. And then if it's greater than, draw up. If it's less than, you would draw down. And whichever side of this line that you just drew an arrow on, that's the side that you want to shade. So, ta-da! This is the side that would be shaded. One of my least favorite things in math to do on a computer instead of paper is shade, because this is, I'm going to be honest, this looks pretty gross to me, shading wise. But if I was doing this on paper, it would look so much better. So this is greater than, not equal to, so this is how we draw it. On 14, we have y is greater than or equal to -5. Now, y lines that don't have an x at all are horizontal lines. So this would be a solid line at -5. If it was x is greater than or equal to -5, it would be a vertical line that goes through -5. And a lot of people feel like this is backwards than how it should be, because the y-axis goes up and down. So why wouldn't the line y is greater than or equal to -5 go up and down? It has to do with the fact that it's telling us the points for the y value on this line are at -5. And our x value can actually be anything. So think about, where is 2 -5? Where is 0 -5? Where is -2 -5? Okay, so that's how this becomes a horizontal line whenever it has a y but not an x. Now, if we want to shade greater than or equal to, like I said, that means above. So that would be this side of our line. Hopefully it's pretty easy to you in this one, that it's greater than and is above, and which side that is. Less than would have been below. We didn't have that one happen. All right, we are solving systems of equations. These first two say to solve by substitution. The next two say solve by elimination. So solving by substitution is the method where you solve one of the two equations for either x or y, whatever is easiest, then you plug it into the other equation. So for instance, if I look at this and say, oh, this y would be really easy to get by itself because all I have to do is subtract 6x to both sides, then that would be a really great place to start. Now, you may be looking at this and say, oh, but I don't really remember substitution, but I remember elimination, so can I just do elimination on it? Because it would be so easy to do elimination on this problem. And my answer to you would be, it is important to be able to do both methods, and unfortunately, if it's easy to use substitution on, it is easy to do elimination on, if we're talking about linear systems. But there will come a day, not very far in your future, in Algebra 2, where you are solving different systems than these, and it will be more difficult to do elimination than substitution. And so you might as well practice right now on problems that are easier so that you have the hang of it for later. What I've done, as I was on a soapbox a second ago, is I've said if y equals 2 minus 6x, then this y also has to equal 2 minus 6x. So I'm going to put 2 minus 6x right here and rewrite the second equation. If it helps you to think of this as a -1, then please do. We're going to distribute to this parentheses, so -6x minus 2 plus 6x equals 3. We're going to do -6x plus 6x, which actually cancels and gives us -2 equals 3. This is a special system. It is not a system that gives us a normal answer, which, by the way, normal answers for this are an x and a y, which makes a point. But this is saying, hey, -2 equals 3, which is not true. -2 does not equal 3, so our answer here is no solution. That is one of the two special cases you can have. Most of our problems should end up being points, like 2,5 or something like that. But one special case is no solution, where the variables go away and then you get a statement that's not true. The other situation that we can have happen that is not a point is infinitely many solutions, and that's where our variables cancel, but we have something that is true, like 0 equals 0. Okay, on 16, I want to solve for a variable. I'm going to pick x here. It doesn't matter which one you solve for. You just want to try to pick what you think will be easiest, or just pick something so that you're not just stuck staring at the problem. If I subtract y over, I get x equals 5 minus y. So I'm going to put that here where this x is. 8 times 5 minus y, and then keep writing the equation. We are going to distribute this 8. We could divide by the 8. I did that earlier on those distributive property problems. And so you certainly can do it here, but you would have to be careful and divide this by 8, and this by 8, and this by 8. And so if you're willing to go through and do that, then that's fine. I didn't actually distribute the 8. I bet you're thinking, wow, what are you doing right now? I didn't actually distribute that 8. So 8 times 5 is 40. 8 times negative y is negative 8y. And then we continue writing it. So now, negative 8y minus 8y does not cancel. It adds to get negative 16y. And then we take the 40 and subtract it over. And get negative 16y equals negative 16. So then we divide both sides by negative 16. This, when you did it the first time in Algebra 1, was at that point in time the longest problem you'd probably done in your life, math-wise. And so this feels like a lot, especially if you've been doing nothing all summer and now you're trying to get ready for school. But this is only half of our answer, because now we know that y is 1. Now we want to know what x equals. So the best place to do this is right here where we already solved for x. What we can do is we can put a 1 where that y is and say, well, 5 minus 1 is 4. So that means x equals 4. And then we write our answer actually as a point, because what's happening here is these are two lines that are crossing, and they are crossing at the point 4, 1. So a lot more work when we were trying to actually find an answer versus having no solution, but there it is. Now we're going to do elimination. The deal with elimination is you get to your first answer faster than on substitution, but then to get the second answer is a little more work. So people typically have a preferred way of doing it, and mine, it depends on the numbers, which one I would prefer to do, substitution or elimination. So kind of the size of the numbers. I guess as the numbers get bigger, I would rather use substitution if there's still a variable that's relatively easy to solve for. But anyway, to use elimination, we want to look at our x's and our y's and say, which of these can I make be the same number in front of that variable? For instance, a negative 6 and a negative 12, I can turn both of those into a 12, because I can take the negative 6 and multiply it by 2, and I'll have 12. But I don't just want it to be the same exact number. I actually want them to be opposite signs from each other. So I want to multiply this first equation by negative 2. That is not the only way to do elimination. Like, there are other numbers we could pick, but at least in this case, we are pretty much stuck multiplying both equations by something. Sorry, we're either stuck multiplying both equations by something, or we have to use this negative 2 that we've got. So I'm going to distribute the negative 2 to this first equation. So that gives me positive 12x minus 4y equals 44. And so the x's cancel. 9y minus 4y is 5y. 6 plus 44 is 50. And then we divide both sides by 5 and get y equals 10. See, that was really easy to get our first answer. To get our next answer, which is x, we need to take this 10 and put it into one of the two equations we started with, or this third equation that we got. We need to put it back in and solve for x. So if I pick the first equation, I really like picking the first equation, because then it feels like I'm not having to make a decision myself. I actually just usually pick whatever has the smallest numbers, because that makes it easier to work with. 2 times 10 is 20. That's the first thing we want to do. And then we want to subtract that 20 over to the other side. Negative 22 minus 20 is negative 42. And then I want to divide by negative 6. So x equals 7. That means my answer here is 7, 10. On 18, I'm going to look at x or y and say, okay, what number can I make them both equal? So in this case, it doesn't actually matter which one you look at, because what we would come to is a conclusion to multiply maybe by negative 3 on this first equation. So we'd get negative 6x and plus 9y and negative 18. And then we add the equations together, and in this case, everything cancels. Now, when the x's and y's both cancel, that'd give us 0 left on the left side. 18 minus 18 is also 0. When we have 0 equals 0 like this, you would say that your answer is infinitely many solutions. And I think saying infinite solutions also works, but most textbooks write out infinitely many solutions. Most teachers, I don't actually know. I don't know that many teachers to be able to say most teachers. The teachers I know also like infinitely many solutions as the phrase, because what's happening here is there are a lot of points that work for this. Infinitely many points work for this set of equations. Not every single point you can think of, not like 0, 0 wouldn't work, for instance, because when you play it in, you'd get 0 equals 6. So that doesn't work, but there are a lot of points that do work. Okay, 19 through 22 have us reviewing exponent rules. So the key with understanding exponent rules is to think of v to these powers as v written out that many times. So v cubed is 3v's, and v to the fourth is 4v's, and v to the second is 2v's. So together we have 9v's. So you can either do that by writing them out, 3v's, we've got 4 more v's, and then 2 more v's. Oh, now I can count them and I have 9. Or you can remember the rule, which is that when you're multiplying two things together, their exponents add. The numbers in front here, 3, 4, and 2, are normal numbers that we're multiplying together. So we need to say, what's 3 times 4 times 2, which would equal 12. So our best answer here is 12v to the 9th. On 20, we are being asked to square 2k to the negative 2. When we square, and there's technically two things in here, a number and a variable, we want to do 2 squared, and we also want to do k to the negative 2 squared. When we are squaring things, we multiply the numbers together, because what we're saying is that I have k to the negative 2, actually 2k to the negative 2. I have that twice. That's what squaring means. And so that means that I'm going to do 2 times 2, which is 2 squared, but I'm also going to do k to the negative 2 and k to the negative 2, which when you add those together is negative 4. The same idea is doing negative 2 times 2 gives you negative 4. Now, we are going to write our answer with only positive exponents. So 2 squared is 4, but what we want to do with the k is we want to move the k down to the bottom, because that's how we turn negative exponents into positive exponents in math. And all it is that act of moving it down to the bottom is what changes it to a positive 4. And it does not move the 2 squared, which has turned into a 4. That 4 gets to stay on top because the 4 has a positive exponent of 1. Sometimes we think of these two things as being attached on top, and they are in some ways, but not as far as whether we can move it down to the bottom or not. They're not attached like that. So our answer is 4 over k to the 4th. On 21, we have n to the negative 1, and then it's to the negative 4th power. So this is where we want to multiply these together. Negative 1 times negative 4 is a positive 4. So that's n to the 4th. And then we have a positive exponent, so we don't need to move it anywhere. X to the 0 is special because x to the 0 equals 1. So essentially on bottom we're saying 2 times 1, which is just 2. Really, if you have a bunch of stuff and something is to the 0 power, it's like you can just kind of cancel that out. If it's the only thing on top or bottom, you'd have to put well, on top, if it's the only thing on top, you'd have to put a 1 there as a placeholder, but otherwise you can mark it out. Now, the 3 and the 2 here don't simplify, so we need a 3 on top and a 2 on bottom in our answer. There's nothing to cause those to move, but this x to the negative fourth, that actually needs to move down to the bottom to give us a positive exponent on the bottom. So this would be our best answer, 3 over 2x to the fourth. All right, now we've got some operations with polynomials. 23 is adding. I know that it's adding because of the plus sign in between. So the way these problems are designed is it's intended to make you think this is a polynomial and this is a polynomial, and I am adding those polynomials together. This is not where you do some kind of fancy distributive property thing. We just want to actually find like terms. And so I would actually start by using the biggest exponent, because then we'll also end up in standard form. So look at this, say, okay, the biggest exponent is the 3's. So I'm going to do 7x cubed plus 2x cubed, which together makes 9x cubed. So in my answer, I need a 9x cubed. And then you could even mark those out to show yourself that you've already dealt with them. Then look for the next biggest exponent. So this squared, negative 3x squared, doesn't have anything to add with, so it just gets to stay minus 3x squared. Now I'm going to look for first powers, which are no powers at all, but still have an x. So x plus x is 2x. And so then those go away. And then all I have left is this plus 7, which doesn't have anything to add with. So this is the answer to these two polynomials added together. It's also in standard form. A reminder, standard form is where the biggest exponent is first and then it counts down. That's a thing that we like to do in math, is write things in standard form. When we are subtracting, the only difference is that instead of saying 8n squared plus 7n squared, we're going to say minus. I had to find two that actually connected, because 7n to the fourth doesn't have anything to change it, so it would stay 7n to the fourth. This 4n cubed, though, that we have right here, we are supposed to be subtracting 4n cubed, so that means it's minus 4n cubed. It's no longer a plus 4n cubed. One way that people will do this to help them is they'll actually distribute the negative and say, let me just change these so that they have different signs. If any of these were negative, we would have ended up changing them to a positive when we distribute. And then now let's not think about this at all. Let's use these. And so that's how we would end up with this negative 4n cubed instead of a positive 4n cubed. So 8n squared and negative 7n squared together make a positive 1n squared. Distributing the negative actually lets us think about this as adding like terms again, which is nice. So then I look at 7n and negative 3n, and that gives me a positive 4n. So that's my answer. For products, we either use the acronym FOIL or we use the distributive property. And it is up to you which one you use, because they actually do the exact same thing. It's just the way you're thinking in your head. The acronym FOIL, that's not an F. The acronym FOIL stands for first, outer, inner, last, and it's talking about the terms we put together. So first is the first term in each parentheses, which is p and p. So we do p times p and get p squared. O stands for outer, so we do p and negative 5, which is negative 5p. Now if you look at that, that looks exactly like the distributive property. Because it is exactly like the distributive property, we would distribute the p to both of those. Then if you're thinking of it like the distributive property, we also need to distribute the negative 3. So this is the I and the L part of FOIL. Inner are these two inside things, the things farthest inside our problem. So the negative 3 and the p, which is negative 3p. And inside, negative 3, no, I just did inside. Last is the negative 3 times the negative 5, which is positive 15. A lot of times when you FOIL, but not all the time, just like 95% of the time I feel like, the middle terms end up being like terms, and so we add those together. So p squared minus 8p plus 15 is our answer. Now, take a look at how this worked, that we went from two parentheses to a quadratic trinomial because a few problems down the road here, we're going to do the opposite and we're going to try to factor something. And so we're going to take something like p squared minus 8p plus 15 and try to turn it back into p minus 3 times p minus 5. So just think about that. Get excited. All right, 26. So you can think about it like FOIL. You can think about it like the distributive property. They literally look the same as you write them down. FOIL is just trying to help you keep track of what you have and haven't done, because I think it makes it more obvious that there are 4 things that you should end up with, and then you add the middle ones together. So 4r times 3r is 12r squared. 4r times 7 is 28r. Negative 3 times 3r is negative 9r. And negative 3 times 7 is negative 21. We're going to add these middle terms together, or subtract them. 28 minus 9 is 19r. So 12r squared plus 19r minus 21. So here we start a section that says factor the common factor out of each expression, and then we end up with factor each completely. So factoring is where we take what we have and we split it up into things that multiply together to get it. You've been factoring for a while. You have in the past said like the factors of 24 and either made a factor tree and done the prime factorization, or even just making a list of like 3 times 8, 4 times 6, that sort of thing. That's factors. It's in some way splitting things up into what multiplies to get it. So this is telling us to factor the common factor out, or I would argue probably the greatest common factor out. And so we look at these 3 terms and we say, I can divide them all by 6. And if you wanted to, you could divide them all by negative 6. We don't have to, but we can. So I'm going to say, I'm going to divide all of these by 6. That 6 doesn't go away because I want my answer to be the 2 things that multiply together to get what my original problem was. So I'm going to say 6 times what gives me my original problem. Well, 6 times what equals negative 30. The answer to that is negative 5. That's division that's happening there. 12b divided by 6 is 2b, or not to be. Negative 24 divided by 6 is negative 4b squared. And so they didn't have it in standard form, so there's no reason for us to go out of our way to put it in standard form unless we just want to. You could also take out a negative if you wanted to. That would make it a positive 5, a minus 2b, and a plus 4b squared. That's also fine. Neither of these are better answers necessarily than the other. You just want to make sure if you take the negative out, it changes all the signs, not just the first one. And also not just the negatives. It also has to switch the positive to a negative. On 28, there's a number in common, but there's also k's in common. All of these have at least k squared. The number they have in common is 2. So we're going to divide everything by 2k squared. So negative 10k squared divided by 2k squared is negative 5 without a k squared anymore. 14k cubed divided by 2k squared is 7k. And 14k to the 4th divided by 2k squared is 7k squared. Now, these answers are pretty easy to check because you would just use the distributive property. If you distribute and you don't get what you started with, then somewhere something went wrong. On 29 here, it says factor completely. We definitely want to check, especially as big as these numbers are, do all of these divide by something? I keep doing really bad lines here. I'll change colors while I'm at it. All right, do all of these divide by, I don't know, maybe a 4? Because that would be super awesome. That would give me v squared and 18v and 80. Now, this is factor each completely. Let's look at this parentheses inside and see, is there a way to split this into 2 parentheses? And there is, because we're going to say what multiplies to get 80 that adds to get negative 18, which would be negative 8 and negative 10. And then this 4 drops down and is still in front. This is my answer. Now, this in particular might be something that you've forgotten from Algebra 1, and so you want to go and look up videos about how to factor. I'll go ahead and I'll leave some in the description of this video in case you want to check out some of my videos on factoring. But there's factoring videos, I'm sure, all over the place on the internet. So that you can definitely remember how to do this, because this is going to be pretty important as you're going through Algebra 2. That kind of after the first time you guys go over it again, if not before, it's going to be expected that you know how to do this, and it's going to keep cropping back up just when you least expect it, or all the time. So you should expect it all the time. It happens a lot. All right, 30. Let's look and see if there's something in common. There's an x in common, so that'd give us 7x minus 10. And that's actually all we can do on this one, because now if there's not an x squared left and there's not any common factor inside the parentheses, then we can't go any farther with our factoring. If this still had an x squared and had something else going on, then we would keep going, but that's all there is to it. So I hope you have enjoyed this review. I hope you enjoy learning Algebra 2 this year. You've got a lot of fun stuff to go through in math, some neat connections to make that you'll start to see. And this is not intended to be a, here are all the things you did in Algebra 1, because you took Algebra 1 for a whole year. There's a lot of other stuff in Algebra 1. For instance, nowhere here did we do the quadratic equation, or quadratic formula, I mean, and that's a thing in Algebra 1. So this is not meant to be an exhaustive list, but this is a list of things that if you know these things, you'll have a good start, hopefully, to your Algebra 2 year. So good luck.